Hello students and friends. This video is a continuation of the past upload on electromagnetism and electromagnetic induction. This time we are concentrating on analyzing problems involving electromagnetic induction, applying Faraday's and Lenz's laws. So stick around, watch and learn. Question number 1. Imagine moving along the axis of the current carrying loop in the figure, starting at a point well to the left of the loop and ending at a point well to the right of the loop. Question letter A. How would the magnetic field vary as you move along this path? The options are: number 1, it would be the same at all points along the path. Option number 2, it would increase and then decrease. Option number 3, it would decrease and then increase. Question letter B. Would the magnetic field direction vary as you move along the path? Alright, so our illustration here, we have the current carrying loop as shown here in the figure, and there is current that is induced in the loop. As shown, the direction of the current induced is counterclockwise. Alright, so the magnetic field lines are represented by the arrows. Okay, first question, how would the magnetic field vary as you move along this path? So starting at a point to the left of the loop, and then you move through the loop, okay, ends at a point to the right of the loop. All right, so how do you describe the magnetic field, the magnitude of the magnetic field as you move along this path? You'll have the answer and explanation in a short while. All right, so the answer to question letter A, how would the magnitude of the magnetic field change as you go from a point to the left of the loop, all right, until you uh, reach a point to the right of the loop? So the answer is the magnetic field would increase as you move to the right, reaching the maximum as you pass through the plane of the loop. And as you move beyond the plane of the loop, the field magnitude would decrease. And this is clearly indicated by the presence of the magnetic field lines. You will notice that as you approach the point exactly at the plane of the loop, you will notice that the magnetic field lines are very much close to each other, indicating that the magnetic field lines or the magnetic field, okay, is greatest or maximum at that point exactly at the center of the loop. And as you go, all right, to the right, what happens is the magnetic field lines, okay, become farther apart from each other, suggesting that the magnitude of the magnetic field is decreasing. Now for question letter B, how about the direction of the magnetic field? What happens? Does it change or not? The answer is no, there is no change in the direction of the magnetic field. The direction of the magnetic field will still be to the right at all points along the path. Question number 2. A single circular loop of wire with radius 2.40 cm lies in the xy plane. There is a uniform magnetic field that changes at a steady rate from 0.140 Tesla in the positive z direction at time equals 0 to 0.110 Tesla in the negative z direction at time equal to 2.00 seconds. Take the area vector for the loop to be in the positive z direction. Alright? So before I read the question, let's go back to the illustration first. So we have the three axis. You have here the x-axis, the y-axis, and the positive z-axis. It says that the circular loop, okay, lies in the xy plane. Alright? So we can imagine that the area vector, alright, at t equals 0, we can imagine that the magnetic field is directed, according to the problem, it is directed in the positive z direction. Alright? So the magnetic field is perpendicular. Alright? Perpendicular to the plane of the circular loop. Alright? And if you're going to represent the area vector, okay, it's going to be towards the positive z direction at the initial time equals 0. But at time equals 2 seconds, okay, according to the question, the magnetic field is now directed towards the negative z direction. Alright? So, there is completely a reverse in the direction of the magnetic field. Originally directed towards the positive z direction. Then, after 2 seconds, alright, it has been reversed to negative z direction. Alright? And questions are, for letter E, you're asked to find the magnetic flux through the loop at the initial time equals 0 and the magnetic flux at time equals 2.00 second. Alright? So, the formula for determining the magnetic flux, represented here by the Greek letter phi, is just equal to, alright, the product, alright, the product of the magnetic field, okay, to be multiplied by the magnitude of the area vector A. Alright, so we are just describing here the scalar product, alright, of the two vector quantities. The first vector is the magnetic field, alright, which originally is directed towards the positive z-axis, and then that will be multiplied by the area vector A, which at time 0 is also directed towards the positive z-axis. Alright, that's the first one. Okay, the second one is at time equals 2.00 second. Okay, what is the magnetic flux? Alright, when the magnetic field has already reversed its direction, right? According to the question, at exactly time equals 2.00 second, the magnetic field B is now directed towards the negative z direction. Alright? But to get the magnitude of magnetic flux, we still follow the same formula. We just multiply, alright, the magnitude of the magnetic field and the magnitude of the area vector A. So these are the formulas that we're going to use in answering question letter A. For question letter B, all right, we are asked to find the magnitude of the induced EMF in the loop while the field is changing. All right. So from 0 time to 2 seconds, there is a steady change in the magnetic field. All right. A change from negative magnetic field whose magnitude is 0.140 Tesla, all right, to a magnetic field whose magnitude is equal to 0.110 Tesla and whose direction has been reversed, all right, from the original positive z direction, it's now towards the negative z direction. The formula for determining the magnitude of the induced EMF, all right, represented here by the Greek letter epsilon, is equal to the negative delta phi. All right. Negative delta phi means the change in the magnetic flux divided by the change in time. All right. So when you say delta phi over delta t, we are just talking about the rate of change in the magnetic flux. We will see the detailed computation for these two questions, A and B, in a short while. So moving on to our detailed computation, for question letter A, the formula for finding the magnetic flux, denoted here by the capital letter, Greek letter P, right? So this is at exactly time 0, at the start. The formula is, we just multiply or get the scalar product, okay, of the magnitude of the magnetic field and the magnitude of the area vector multiplied by cosine of the angle small letter phi, where angle small letter phi represents the angle between the two vectors, the magnetic field B and the area vector A, right? So when we substitute, okay, the magnitude of the magnetic field at time equals 0 is 0.140 Tesla, right? And since angle phi, all right, angle P between the two vectors is equal to 0 degree because they are in the same direction, positive z-axis. The cosine of 0 degree is exactly equal to 1. That's why um, our what you call product or the scalar product of B and A is just equal to 0.140 Tesla to be multiplied by the magnitude of the area, which is pi to three significant figures, 3.14, and the square of the radius, which in meter is equal to 2.40 times 10 to the negative 2 meters. So doing our math, we get this magnetic flux, okay, capital letter phi equals 2.53 times 10 to the negative 4 Weber. Weber is just equal to Tesla meter squared. Okay, in the SI system, the unit for magnetic flux, okay, can either be Tesla meter squared or simply the unit Weber. So take note that this magnetic flux is directed in the positive z direction. Likewise, getting the magnetic flux at time equals 2.00 seconds. So we use the same formula. But as mentioned in the problem, at time equals 2.00 second, the magnetic field has decreased its magnitude. All right? It has decreased to 0.110 Tesla. Okay? And likewise, its direction has become negative z, or towards the negative z axis. Now, if that is the case, we have a situation where the angle phi between the two vectors is, the angle phi is equal to 180 degrees. In which case, the cosine of that angle 180 degrees is equal to negative 1. All right? So it's just proper for us to put the negative sign here because this represents the direction of the magnetic flux, which is directed to the negative z uh, axis. Okay, negative 0.110 Tesla, still to be multiplied by the magnitude of the area or area vector, 3.14 to 3 significant figures of the phi value, and the square of the radius in meters. Doing our math, we will get the value for capital letter phi equal to negative 1.99 times 10 to the negative 4 Weber. Alright? So compare this with the original magnetic flux. At time 0, we have positive 2.53 times 10 to the negative 4 Weber. Then at time equals 2.00 second, the magnetic flux, okay, has now become negative 1.99 times 10 to the negative 4 Weber. So, this brings us to question letter B, which is asking for the induced EMF denoted by the Greek letter epsilon. And the formula for getting the induced EMF is just equal to negative delta phi divided by delta t. This is based on both Faraday's law and Lenz's law. All right. The negative sign, uh, here emphasizes what Lenz's law is telling us, that an induced current or EMF always tends to oppose or cancel out uh, the change that caused it. That is what Lenz's law is telling us. So to emphasize Lenz's law, we put here a negative sign. Negative delta P divided by delta T. So when we substitute, all right, the value of delta phi is simply the difference between the final magnetic flux, that is at time equals 2.00 second, okay, and the magnetic flux final is equal to negative 1.99 times 10 to the negative 4 Weber, okay, minus the initial magnetic flux at time equals 0, which is 2.53 times 10 to the negative 4 Weber, and we will get the delta phi, or change in the magnetic flux, equal to negative 4.52 times 10 to the negative 4 Weber. Alright? Take note, there is a double negative. So negative, then parenthesis, negative 4.52 times 10 to the negative 4 Weber, still to be divided by the time interval, which is 2.00 second. So doing our math once again, we will get the induced EMF equal to positive 2.26 times 10 to the negative 4 volts. This is the magnitude of the induced EMF. All right. Now, going back to our illustration, where we have here the circular loop, which is lying on the XY plane, and the direction of the magnetic field, capital B, all right, is towards the positive Z axis. All right. And then the vector or the area vector, capital A, is also directed towards the positive z-axis. That angle phi, all right, which we use in our computation, it happens to be equal to 0 degree at time equals 0, all right, and at time equals 2 seconds, this has changed to 180 degrees. Now, supposing we don't know yet the direction of the induced EMF, all right, and we make use of a convention in determining that direction of the EMF. We call it the right-hand rule. So according to the right-hand rule, if we will let our right hand, the thumb of our right hand represent, okay, represent the area vector, all right? So you have to position your right hand such that your thumb is pointing towards the area vector A, all right? In the x, y, z coordinates that is directed to the positive z-axis. Okay, so both vectors A and B are perpendicular to the plane of the circular loop, which is lying in the xy plane. All right. So what happens is, for you to determine the direction of the induced EMF, you have to check first what is happening to your uh, change in the magnetic flux. Initially, the magnetic flux is positive. All right. Positive meaning it is, as mentioned in the problem, directed to the positive z-axis. That is what is meant here by uh, angle phi, or the magnetic flux greater than 0. That means it is positive. The flux is positive. And from 0 to 2 seconds, what is happening to that magnetic flux? It is becoming less positive. All right? The change in the magnetic flux became negative. As shown in our earlier computation, the delta phi became negative 4.52 raised to the negative 4 Weber. So, if that is the case, then uh, if you are going to curl your four fingers, all right, while your thumb is pointing towards the direction of the area vector, the curling of your four fingers, all right, will represent the direction of the induced EMF. And in this case, it is directed counterclockwise along the circular coil. All right? So this description of the direction of the induced EMF using the right-hand rule agrees with our computation using Faraday's and Lenz's laws. Now, supposing, just in case the change in the delta phi, right, is still positive, all right, what happens here is that it is becoming less positive. In fact, it becomes negative. What if it is positive? So that would simply mean that the direction of the EMF is opposite to the direction of the curling. All right. So if here the direction of the curling is counterclockwise, such that we were able to conclude that the EMF is directed counterclockwise, all right? The opposite is if in case the change in the delta phi, all right, is it is positive. Okay, a positive delta phi would suggest that the direction of the induced EMF is opposite to the curling of the four fingers. I hope that is clear. All right. This is now our last question. Question number 3. A circular coil with 455 turns of wire has radius 5.00 centimeters and resistance 14.5 ohms. The area vector of the coil points in the positive z direction. The coil is in a region of uniform magnetic field that points 20.0 degrees from the positive z direction. The magnitude of the field is initially 0.0600 Tesla and decreases at a rate of negative 3.00 times 10 to the negative 3 Tesla per second. Question is, find the magnitude of letter A, the induced EMF, and letter B, the induced current in the coil while the field is changing. So, the solution to this problem for question letter A, finding the magnitude of the induced EMF, okay, we will first calculate for the magnitude of the area vector A, and that is just equal to pi r squared, all right, to three significant digits. 3.14 is the value for pi times the square of the radius. We are given r equals 5.00 centimeters. So in meters, that is 5.00 times 10 to the negative 2 meters. Square that, multiply it by 3.14, we get the magnitude of the area vector, which is 7.85 times 10 to the negative 3 meter squared. Right. So we will continue with our solution in just a short while. Alright, so moving on with our calculation, we have here the rate of change in the magnetic flux. Delta big phi divided by the time t can also be expressed as delta b, okay, over the time t to be multiplied by the area vector A. We are given in the problem the rate of change in the magnetic field, which is negative 3.00 times 10 to the negative 3 Tesla per second. Okay, that is delta B over T. Okay, we call it the rate of change in the magnetic field. And then we are also given we have calculated earlier the magnitude of the area vector, which is 7.85 times 10 to the negative 3 meters squared. All right? And the area vector A and the magnetic field happens to have an angle of 20 degrees. All right? 20 degrees from the positive C direction. So this delta B over T multiplied by A still has to be multiplied by the cosine of 20.0 degrees. So simplifying, we get the value for the change in the magnetic flux equal to negative 2.21 times 10 to the negative 5 Weber per second, because Tesla meter squared is Weber, but there is still the unit per second. So this becomes Weber per second. All right? It has a negative sign. So in other words, the change in the rate of the magnetic flux is in the negative z direction. So moving on now to question letter A, which is to find the induced EMF. Epsilon is equal to negative multiplied by number of coils or turns. All right? The letter capital N represents the number of turns. of the coil, of course, to be multiplied by delta P over T, or the change in the rate of the magnetic flux. Substituting, we have 455 multiplied by 2.21, okay, multiplied by or times 10 to the negative 5 volts, since Weber per second is the same as volt. All right. What happens why this became positive? It is because um, delta P over T is supposed to be negative, but in the formula of Lenz's and Faraday's laws, there is a negative sign. So, negative of negative, this becomes positive. Simplifying, we get the value for the induced EMF equal to 1.01 times 10 to the negative 2 volts. Alright, so that is the answer to letter A, which is the magnitude of the induced EMF in the coil. And moving on to the question letter B, which is determining the current induced in the coil, we simply divide the induced EMF, all right, by the given resistance, okay, of the coil, that is small letter r. So substituting our induced EMF is 1.01 times 10 to the negative 2 volts divided by 14.5 ohms. We get the value or magnitude of the induced current in the coil equal to 6.97 times 10 to the negative 4 amperes. So once again, our answer to letter A, the induced magnitude of the induced EMF equal to 1.01 times 10 to the negative 2 volts. And answer to letter B, magnitude of the induced current equal to 6.97 times 10 to the negative 4 amperes. So that's it. We are done with our computations. So that ends our video tutorial. Thank you very much, as usual, for your indulgence. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.